Hi, this is the Science Chef. Today we'll be learning about angular projectile motion in the third part of a series on projectile motion. In this video, we'll explain how to derive the important formulas and equations of angular projectile motion with some worked examples. In our tutorials on definition of projectile motion and vertical projectile motion, we learned about the concept and types of projectile motion and the equations of vertical projectile motion respectively. If you'd like to watch those videos, we have added the links in the description. Consider a bullet fired into the air, inclined at an angle theta to the horizontal plane and allowed to move under the influence of gravity. It undergoes two independent motions at any point in time, the horizontal and vertical motions, because the effect of gravity on the vertical and horizontal planes are not the same. While the force of gravity will influence the vertical motion of the body, it has no effect on the bullet's horizontal motion. Therefore, from our knowledge of resolution of vectors, the velocity u of the body will be resolved into two components: the horizontal component u cos theta and the vertical component u sin theta, and the resultant velocity will be the square root of ux squared plus uy squared. Just like we did in vertical projection, in deriving the equations and formulas of angular projectile motion, we will also apply the basic equations of motion displayed on the screen. Recall that u is the initial velocity in meters per second, v is the final velocity in meters per second, t is the time taken to cover a given distance in seconds, s is the distance covered in meters, while a is the acceleration in meters per second squared. Using the upward flight, let's see how to derive the formula of angular projection, starting with the maximum height. The maximum height is the highest vertical distance attained by the projectile when measured from the horizontal projection plane. The bullet leaves the gun at point P with an initial vertical velocity of u sin theta and a horizontal velocity of u cos theta. As it moves up, its vertical velocity decreases steadily until it gets to point Q, where its final velocity becomes 0. Meanwhile, its horizontal velocity remains unchanged throughout the upward journey. The distance from point O on the horizontal plane to point Q on the vertical plane is the maximum height h attained by the bullet. If we substitute the values of v, u, and s in the third equation of motion with v sin theta, u sin theta, and h respectively, bearing in mind that acceleration due to gravity for an upward motion is always negative, that is, a equals negative g, then equation 3 becomes v sin theta squared equals to u sin theta squared minus 2gh. If we substitute the value of v as 0 at the maximum height and solve for h, then equation 4 will reduce to h equals to u squared sin squared theta all over 2g, where u sin theta times u sin theta equals u squared sin squared theta. Equation 5 is the formula for calculating the maximum height attained by a body projected into the air at an angle theta to the horizontal with an initial velocity u in meters per second. Next is the time of flight. In angular projection, the time of flight is the time required for the projectile to return to the same level from which it was projected. In deriving the time of flight, we will first determine the time for the upward motion, that is, the time it will take the bullet to move from point P to Q, and then add it to the time for the downward motion, which is the time it will take to move from point Q to R. Usually, T1 and T2 are always equal since the body covers the same distance in its upward and downward motions. So we can simply multiply the time for the upward flight by 2 to get the time of flight. To derive the time of flight, we will use equation 1, which connects v, u, a, and t. If we substitute the values of v, u, and a as v sin theta, u sin theta, and negative g respectively, then equation 1 becomes v sin theta equals to u sin theta minus gt. Substituting the value of v as 0 at the maximum height, then equation 6 becomes t equals to u sine theta over g, which gives us the time taken by the bullet to reach the maximum height, or the time it will take to fall from the maximum height to the plane of projection. Therefore, multiplying equation 7 by 2 gives us the formula for calculating the time of flight for a body projected into the air at an angle theta to the horizontal with an initial velocity u in meters per second. Similarly, we can derive another formula for calculating the time the bullet takes to reach the maximum height by applying the second equation of motion, s equals to ut plus half at squared for the downward motion. If we substitute the value of u, s, and a in this equation with u sine theta, h, and g respectively, then equation 2 becomes h equals to ut sine theta plus half gt squared. Recall that at the maximum height, the initial velocity for the downward motion is 0. So if we substitute that into equation 9 and solve for t, we will obtain t equals to the square root of 2h over g. Equation 10 gives the formula for calculating the time it will take the projectile to reach or fall from the maximum height when only the height is given. Multiplying equation 10 by 2 gives us the formula for calculating the time of flight when the height alone is given. The last parameter we'll be considering in this lesson is the range. The range is the horizontal distance covered by the projectile from its point of projection to the point where the projectile hits the projection plane again. In an illustration, the range is distance PR. To derive the formula for range, we will make use of the basic equation for calculating distance, which is velocity multiplied by time. In this case, our distance is the range r, while velocity is the horizontal velocity ux, and time is the total time of flight, capital T. We are using the time of flight because for the bullet to move from P to R, it will use the time for both the upward and downward flights. Recall that time of flight is calculated as 2u sine theta over g, and the horizontal velocity is u cos theta. Therefore, substituting this into equation 12, the range will be equal to u cos theta times 2u sine theta over g. From our knowledge of trigonometric identities, we know that sine A plus B equals sine A cos B plus cos A sine B, and sine A plus A equals sine A cos A plus cos A sine A, which is equivalent to 2 sine A cos A or 2 cos A sine A. Therefore, using this knowledge, we can replace 2 cos theta sine theta in the above equation with sine 2 theta. Hence, equation 13 becomes r equals to u squared sine 2 theta over g, which gives us a formula for calculating the range covered by a projectile launched into the air at an angle theta with an initial velocity u in meters per second. Let us now look at a summary of all the formulas we have learnt in this lesson so far, starting with the horizontal velocity. The horizontal velocity ux is calculated as u cos theta, and it is maximum when theta is 0 because cos theta is 1. Next is the vertical velocity uy, calculated as u sine theta, and its maximum value is when the angle of projection is a right angle because sine 90 degrees is 1. Next is the maximum height h, given as u squared sine squared theta over 2g. The possible highest height that is attainable by a given projectile will be when sine squared theta equals 1, and that will make theta to equal 90 degrees. Next is the time taken to reach the maximum height small t, calculated as u sine theta over g or square root of 2h over g, and its value is maximum when the angle of projection is 90 degrees. Next is the time of flight, capital T, calculated as 2u sine theta over g or 2 times square root of 2h all over g. Its maximum value is also obtained when the value of theta is 90 degrees. Finally, the range R is calculated as u squared sine 2 theta over g. The maximum range can only be attained when the projectile is launched into the air at an angle of 45 degrees, because at that value sine 2 theta equals sine 90 degrees, which equals 1. Let's now see how to apply this formulae by solving some examples. Example 1. A stone propelled from a catapult with a speed of 50 meters per second attains a height of 100 meters. Calculate 1. The time of flight, 2. The angle of projection, 3. The range covered. From the information provided in example 1, we are given the initial velocity. We are given the initial velocity u as 50 meters per second and the height h as 100 meters, and asked to calculate the time of flight, capital T, the angle of projection, theta, and the range covered, R. To calculate the time of flight, we first calculate the time it will take the stone to get to its maximum height, or the time it will take the stone to fall from its maximum height to the plane of projection, using the formula T equals to square root of 2h over g. Since we are only given the height, we don't know the angle of projection, so we cannot use u sine theta over g. So you substitute the value of h and g. Our g here is 10 meters per second squared, but it's a constant. Substitute the values of our h and g into this. That will be square root of 2 times 100 meters all over 10 meters per second squared. So if we solve for this, we'll get 4.47 seconds. Now to now get the time of flight, we'll multiply this value by 2. So our time of flight will be what? 2 times 4.47 seconds, which is 8.94 seconds. Now that we know the time of flight, we can easily calculate our angle of projection, theta. Using the formula time of flight equals to 2u sine theta over g. So we'll make sine theta subject of formula, and that will be gt over 2u, and then substitute the values of g as 10 and t, a calculated value of t of 8.94 all over 2 times 50, which is our initial velocity. If we evaluate this, we obtain that sine theta equals 0.894. So to now find theta, we'll take the sine inverse of both sides of that value of the sine inverse of this of 0.894 gives us approximately 63.4 degrees. So our angle of projection, or the required angle of projection, is 63.4 degrees. Find the range covered. That's capital R. We use the formula for range, which is R equals to U squared sine 2 theta all over G. And then substitute the values of U, theta, and G into the equation to obtain 50 squared times sine 2 times 63.4 degrees all over 10. Evaluate this. This will give us 2,500 times sine 126.8 degrees all over 10. That will be 2,500 times sine 126.8 degrees is 0.8007. So all over 10. This will cancel out this. You are left with 250 times 0.8007, which gives us approximately 200.18 meters as the range that will be covered by the stone. It's now your turn. Example 2. A gun fires a shell at an angle of elevation of 30 degrees with a velocity of 2.5 times 10 raised to power 3 meters per second. What are the horizontal and vertical components of the velocity? 2. What is the range of the shell? And 3. How high will the shell rise? In question 2, you are given the angle of projection theta to be 30 degrees and the initial velocity u to be 2.5 times 10 raised to power 3 meters per second, and we are asked to find the horizontal and vertical components of the velocity. That is required. We are required to find ux, uy, and also to find the range that will be covered by the shell, that's R, capital R, and how high the shell will rise, that's the maximum height, h. So 1, to find the horizontal component, horizontal velocity, we use ux equals to u cos theta. So we substitute the values. Our u is 2.5 times 10 raised to power 3 meters per second times cos 30 degrees. That will give us 2.5 times 10 raised to power 3 times 0.8660, cos 30 degrees is 0.8660 all meters per second, and if we evaluate this, we'll obtain 2.17 times 10 raised to power 3 meters per second as the horizontal velocity of the shell. So let's call this 1A. 1B, to find the vertical component of the velocity, which we can also call the vertical velocity. We use uy equals to u sine theta. Substitute the values. It's 2.5 times 10 raised to the power 3 meters per second times sine 30 degrees. This will be 2.5 times 10 raised to the power 3 times 0.5 meters per second. Sine 30 degrees is 0.5, and we evaluate this, we will obtain 1.25 times 10 raised to the power 3 meters per second. So next question, we have to find the range of the shell. To find the range of the shell, we make use of the formula for range, that r is equals to u squared sine 2 theta all over g. And we substitute the values. Our u is 2.5 times 10 raised to the power 3, this will be all squared, times sine 2 times 30 degrees all over 10. So this gives us 6.25 times 10 raised to the power 6 times sine 60 degrees all over 10. Further evaluation gives us 6.25 times 10 raised to the power 6 times 0.8660, which is sine 60 all over 10. If we evaluate this, we'll obtain 5.41 times 10 raised to the power 5 meters as the range covered by the shell, or we can write this as 541,000 meters. Lastly, we are told to find the maximum height. I will make use of the formula for maximum height, which is h equals to u squared sine squared theta all over 2g. Substituting the values, 2.5 times 10 raised to the power 3 raised to the power 2 or raised to the power 2 times sine 30 degrees squared, or sine squared 30 degrees all over 2 times 10. So this is us 6.25 times 10 raised to the power 6 times 0.5 all squared. Remember, sine squared theta is the same thing as sine theta times sine theta. So sine squared 30 degrees is the same as saying sine 30 degrees times sine 30 degrees. So all over 20. Evaluate this, we obtain 6.25 times 10 raised to the power 6 times 0.25 all divided by 20. Further evaluation of this gives us 0.781 times 10 raised to the power 5 meters, which is 7.81 times 10 raised to the power 4 meters. So from our answer, we can tell that the maximum height that was attained by the shell is 7.8 times 10 raised to the power 4 meters. Let's do a quick recap of our solution. We're given the angle of projection and the initial velocity and asked to calculate the horizontal and vertical components of the velocity, the range, and the height. To find the horizontal velocity, we use u cos theta, ux equals to u cos theta. We substitute the values given to us, evaluate, and we obtain 2.17 times 10 raised to the power 3 meters per second. Don't forget your units, very, very important. To find the velocity, vertical velocity, we use uy equals to u sine theta, just like the horizontal velocity. We substitute the values, the given values, evaluate, and we obtain 1.25 times 10 raised to the power 3 meters per second at the vertical velocity. To calculate the range, we use the formula for range, u squared sine 2 theta over g. We substitute the values of u, theta, and g. Sine 2 theta is sine 2 times 30 degrees, which is sine 60 degrees. So sine 60 degrees 0.8660. We evaluate this and we obtain 5.41 times 10 raised to the power 5 meters as the range covered by the shell. And to find how high the shell will rise, we use the formula for the maximum height, which is u squared sine squared theta over what? 2g. We substitute our values, bearing in mind that sine squared theta is the same thing as sine theta times sine theta. So sine squared 30 degrees is the same thing as squaring the value of sine 30 degrees, which is 0.5 squared. 2.5 times 10 raised to the power 3 all squared gives us 6.25 times 10 raised to the power 6 all divided by 20. 2 times 10, 20. If we then evaluate this, we obtain 7.81 times 10 raised to the power 4 meters as the maximum height that was attained by the shell. So if you are able to learn anything from this video, kindly drop a comment, give us a like, share this video, and subscribe to our channel to encourage us to do more videos like this. Remember, life is a battle you cannot lose nor quit. So keep fighting till I see you when I see you.